Now, take it away, Billy.
Okay, yeah. Thank you everyone for coming to my thesis talk. And yeah, so it is finally the time for me to deliver a closing talk, wrapping up my almost 5.5 years of a PhD study. So my topic is about towards robust audiovisual learning. So what is audiovisual learning? It is everywhere in our life. It is deployed on smart cameras, smart speakers. A lot of the social media companies actually doing content filtering using audiovisual learning in the back. So obviously we want them to perform well, and we need them to be very robust to noise. And these are exactly the two questions that I'm trying to solve in my thesis, which is trying to make audio-visual system perform well and also understand and try to, defend against the robust and potentially adversarial perturbations. Okay, so today I'm going to break down my talk into 3 parts. The first part, I'm going to revisit the evolution of the model, the training paradigm. And the second part, we're going to dive more into robustness and understand robustness. Third part is a kind of a pathway to the future and to the state of art, and how do we go forward from here. So the first part, I'm going to mainly revisit the evolution of the model families from CNN families to transformer families, and from the learning paradigm from supervised learning to self-supervised learning. And why did we do that? So, okay, so the main data set for audiovisual learning here, in my thesis, most of my thesis focus on this data set, which is collected by Google. The main author is Dan. He's here right now. He's my committee member. So a few features of audio set. Audio set is 2 million, contains 2 million 10 seconds audio samples. Each one of them are 10 seconds long, but it is very unbalanced. So basically, as you can see, it's a huge, there's a huge long tail, but most of them are music and speech, account for half of them, but it does nicely contain an ontology. Ontology means it is categorized into human sounds, and the labels are sorted in order. So you have human sounds, animal sounds, music, and natural sounds. It does contain a balanced set, but it's only accounting for 1% of the entire number. So it has 20K balanced set, and they're weak label. Weak label means you don't know when does certain thing happen, and it's basically standing for multi-hot labels. So, okay, so before 2020, CNN, like convolution families, were pretty much the de facto architecture for audio set tasks. And we've done a slew of work, particularly early in my PhD study. We've done a number of work using CNNs. Mainly, we understand, the features and different architectures and how to make CNN perform better. But just to give you a taste of how CNN systems were doing, so we were at state of art at 2019 using a CNN model. But the mean, so audio set, by the way, is measured. This is a common shared task. So the performance is measured by mean average precision. Mean average precision is the mean over all the classes, and every class has is average precision. So it's basically the area of the ROC curve. So two takeaway we learned from CNN. So CNN, you only need to remember 2 things to tackle audio. One thing is you need to select the right kernel size. The right kernel size will guarantee you to learn the right filter, because CNNs are learning filters in the back in its kernel. So it's learning just like your man-made, your human designed filters, but there's a sweet spot. If your kernel is too big, then it sees very sparse information, like on the right. But if your kernel is too small, then it learns dispersed filter banks. But so in order, we talked about weak labels. So we only got 1 label for 10 seconds, but we have frame level predictions. So the secret sauce for CNN is to leverage pooling layers to deal with weak labels. So you aggregate all the labels from the frame level to bag level, then you can measure it against the BCE loss, binary cross entropy loss in this case. So that's all you need to know pretty much about the pure CNN architecture in before 2020. But then as we know, like in 2017, 5 years ago, as I started my PhD, Transformer debuted in NLP. Everyone here is very familiar with Transformer, but it took 3 more years, actually 4 more years to let it debut in Vision, which is the 2021 Vision Transformer, and took another year for it to enter into audio. So we also done several works to understand the impact of transformers in terms of applying to audio. But in short, as you can see, this leaderboard growing transformer is able to add a lot more performance onto the audio task. And our work we have done are, mainly understanding what are the components that makes transformer do better, whether being pre-training versus no pre-training, what are the key parameters that you need to care about, mainly learning rate, batch size, all these modern training techniques, how much do they help transformers? If you're interested, you can read my thesis and publications in this domain. But mainly, all you need to know, or the key takeaway for transformer, is that transformer, instead of learning from kernels, it's learning from patch. Patch is the token that transformers learning dwells on. Basically, it learns from the spectrogram patch here. So on the right side, you can see those are the unit tokens of like how transformer learns audio. So each patch is a square blob. The vertical axis is the frequency of the spectrogram, and then the horizontal axis is the temporal stride. So transformers learn using this unit as a token, and transformers main characteristic is relies very much on pre-training. If it doesn't have pre-train to help it to warm start, then it is actually not as good as a equivalent number of parameters of the CNN models. So the problem of the transformer entering the game and everything else is in 2022, this is the left side of the graph is a very chaotic view of state of art in the audio community. As you can see, there are a lot of different work trying to report a benchmark on audio task, on audio set, but the state of art is kind of chaotic because everyone is trying to report their numbers with very different hyperparameters. Someone even report, like there are people reporting on different, well, everyone have their own secret sauce. So it really, we need an apple-to-apple comparison. So we did an apple-to-apple comparison in 2022, which normalized everything into the same learning recipe here. So we developed 4 recipes, A1, A2, A3, A4. That was inspired by a paper called ResNet Strikes Back. But all we were doing is we try to conduct all the experiment in the same fashion, comparing all these network architectures and really see their difference with the same fair starting ground. So what we discovered is that, surprisingly, not only does mainly the 4 recipes we developed here are 2 recipes with larger features, 2 recipes with smaller feature, each with or without pre-train. So that's the key difference of those 4 recipes. So what we discovered is that audio set itself, so we need to be extra careful with the label quality of the audio set. So because in audio set case, like if we measure the performance of the entire audio set versus on the highest quality of the quantile of the data set. So basically, there contains a lot of label noise. If we only evaluate on the highest portion versus all the portions, there are a whopping 9–10% of a mean average precision difference. So you need to take a grain of salt what kind of a eval set you're dealing with. And by the way, we do observe that smaller feature actually don't tank the performance by a lot. It only lower the performance by 2 points of a mean average precision. So really could speed up the experiment a lot. So, okay, so till this point, we have an idea, we have a taste of, say, how does the supervised learning, by the way, all these previous work are supervised with transformer and CNNs. How does the supervised work method, do on audio task? So it is 2023, and we're 3 orders of magnitude behind in both number of trainable parameter and the number of training data in the audio domain versus vision or natural language. So apparently nobody will have enough resources to collect more data. So label data in this case, like it is just very, very expensive or almost impossible. So what do? We resort to self-supervised learning. So the intuitive way of understanding self-supervised learning is let's do something else better or to some very good degree so that hopefully the network will capture the underlying features of the data that you're learning. And then we can let the pre-trained network do something else. The something else in this case is classification. So we do reconstruction first, and then we do classification. And this is the paradigm of masked autoencoder. So the key takeaway for masked autoencoder is we use the masked autoencoder features very high masking ratio up to 70%. So you can see here, like it's pretty much all pitch black with only 30% of the token left for the transformer to learn. And it features the asymmetric encoder and decoder design. So the encoder captures contains a lot more information than the decoder because the decoder will get thrown away in the fine-tuning stage for classification. We only use the fine-tune the encoder for classification. So here's how it works in action. So piece of music, but when it's masked, 70%, you almost hear nothing, right? But when you reconstruct, as you can see, masked autoencoder is all, able to reconstruct perfectly versus ground truth. But if you pay special attention, it does miss little details, but that's not the point here. We're fine-tuning the masked autoencoder to do classification. So another special features when adapting masked autoencoder to audio is that we use a localized attention versus a global attention. Well, transformer is O(n) squared, but even with the newest flash attention, everything is O(n) squared. So why do we need to limit the attention span? And there's a key reason for that. If we use global attention, you see that ghost sample, like the little blob right in front, right in the middle of the graph, that is ghost sample. So if you let it attend to everything, it might hurt because spectrogram has a lot more local dependency than natural languages. So if you use a global attention, then it will create a lot of ghost examples. This is one example, and then the more extreme example will be all of a sudden in a piece of silence, you have a little blob popping up from nowhere. So you want to limit the attention span. So that's a special architecture design change for using a so-called architecture of a swing transformer to limit the attention window. And also, as you can see, in terms of the masking strategy, the audio domain, signal domain motivated masking strategy as a frequency and a temporal masking strategy outperforms random masking strategy. As you can see, the green lines and the red and black lines are all riding above the blue line of a random masking. So they are actually very helpful in terms of fine tuning for audio set task. So, okay, we mentioned there's a balance set of only 1% of the entire data set of a balance set versus the 2 million data set. Let's just give you an intuitive view of training this masked autoencoder on the balance set versus the entire data set. Why do we need the 2 million set, right? So this is the blue graph is the model trained on 20K balance set, and all the classes are sorted by its performance in terms of mean average precision. So you have 527 as the x-axis of all the class label ID, and the red dots are the models that train on 2 million. And you can see there's an obvious trend. Everything is improving, but there are certain classes actually taking a hit, and there are stubbornly low performing, about 100, 200 classes that are staying at a very low region. And what is actually going on? What is actually going on is that because music and speech are so heavily biased, so they're really crushing the performance of other performance like male speech and female speech. Male speech and female speech are always getting, trumped by the prediction of a speech, and then so it occurs the same way for music and versus music instrument and other music genre labels. But the key thing about about mass autoencoder as an SSL, as a self-supervised technique, is that it has potential to scale well because it doesn't need to take all these supervised labels. If you have more labels, if you have more unlabeled data, you could potentially do reconstruction on anything. So it does have a huge potential, and currently it holds a state of art. So we are the second on the leaderboard. The first, the number one is an ensemble solution. So this is really a strong contender. The key takeaway, so for making models perform better, are at this stage we learned basically, modern training techniques, especially pay special attention to learning rate and batch size. The linear correlation between them are very important, and of course, as everyone here at LTI knows, pre-training is crucial. So and then the one more thing is that, as we can see, transformers are gradually eclipsing CNNs. Why didn't we use CNN for masked autoencoder? Because CNN never can take zero masking. If you zero mask CNN, it will arrow out. So CNN is just not a good architecture for this kind of a reconstruction task. And we do see that models with local and global information tend to be the best sort of performing model for audio. Okay, so now that we understand how to build models that perform well, or the training techniques, let's dive into understanding robustness. What do we mean by robustness, and then why do we even care? So early in my PhD, I made a transparent sticker, slap onto a camera, and then it will fool the camera that deploys a ResNet 50 model to believe that a stop sign is a guitar pick. So we didn't do anything to modify the stop sign. It's just by a laser printer, and then you can fool the camera. And then I applied the same idea to audio, and I made a piece of adversarial music, and it sounds like this. It sounds pretty. Alexa. But Alexa never wakes up. Alexa. So what we did is it did a gray box attack. When you play this piece of adversarial music, then Alexa's wake word module is broken. So how do we do this? We train. Well, everyone here train a lot of models, right? So usually we do. So it's all conforming to the mini batch stochastic gradient descent in terms of empirical risk minimization. So we want to minimize the loss function. But if we put our black hat on and be a hacker of machine learning model, then we want to find the adversarial example. What is the adversarial example? Instead of minimizing the loss, we maximize the loss instead. So we're tuning the parameter of the noise to maximize the loss, and then the model will make an error because it's not going to it's not going to the right direction, basically. And what is adversarial training? So adversarial training is basically, there are a lot of math there, conforming to Denskin's theorem and stuff, but I'm not going to touch the details here. But the main idea, all you need to know is adversarial training is given an adversarial example, add them back to your training data. So in the worst case scenario, the inner loop here is the PGD, projected gradient descent, which is finding the worst case scenario. Given the worst case scenario, if you can still minimize your loss, then you're golden, right? You're going to get a robust model, and you're taking a gradient step using this adversarial perturbation as the guidance. That's adversarial training. And here in my thesis, all the adversarial perturbation that we study are called universal adversarial perturbation. Basically applies to entire eval set, and it's not specifically against the one sample. It's against the entire eval set or entire data set. And here the definition, that a little bit of clarification on what is the robustness defined as. Robustness performance, as in my thesis, we care about the robustness performance, the performance under perturbation, which is the model's performance under some noisy condition over the clean scenario. So the denominator here is the normal performance, where the numerator is your model under some influence. And my thesis mainly focus on the type of robustness, which is input robustness. There are lots of other robustness definitions. Is really an overload term, so we want to have a little bit of clear idea. Okay, so this is the landscape or the sort of a overview of what is going on with the adversarial robustness community. So here there are two mainstream of methodology. One is called a certified robustness, and the other is empirical robustness. Empirical robustness is what we just mentioned, basically study the idea of adversarial training. So what's the problem of adversarial training? Apparently we need to retrain. So it's very costly to first find adversarial example and retrain, and it bears a huge computational cost. And not only that, it also makes your adversarially trained model to take a huge hit on clean performance, which means the models without any perturbation. Basically, as you can see on an ImageNet case, if you adversarially train, it only can retain performance of say like 60% of a clean model. So which is a huge penalty. If you want to make your model robust, you kind of need to pay the price to let it be worse performing than a normal model, which is counterintuitive, but it's what do you do to make models more robust? So it's seemingly like, people want to have some theoretical guarantees. That looks like a more promising direction by doing convex relaxation, because, in neural network, all your prediction decision boundaries are like non-convex stuff. So if you do convex relaxation, everything becomes a nice polytope, then you probably can get some upper bound and lower bound of bounding your risk. But also it turns out those are kind of useless in practice, because those bounds are very, very loose. So it really doesn't inform you to do any meaningful design. So it seems like, randomized smoothing is the only one left for this candidate. So what is randomized smoothing? Randomized smoothing is basically training with Gaussian noise. So if you train with a model with a input plus Gaussian noise, it says it will give you a certified bound, and then will also prove to be adversarially more robust. But the problem with that is you need to retrain with Gaussian noise. So it's the same problem as adversarial training, but we will touch up on that idea later in this talk. So, okay, so all these definitions of robustness are pretty much point-wise robustness. You focus on one point, you focus on how does it drift your decision boundary. So in ICAPS 2022, where we had done a sort of a sidetrack study, but it's more focused on a novel idea of class-wise robustness. Can we actually categorize robustness of a certain class in this in this data set? And what are the most promising directions we should look at? We look at two things. We look at convexity and we look at density. Why do we care about convexity? Convexity in the neural network settings, refers to we all know what is convex functions, but convexity in the neural network cases really means if we can take two dots and connect the middle dots of the two embedding space of the dots, if the middle points feed back into the neural network, still output the same label, class label YC, then we call it a convex. So we can do sampling and kind of characterize that classes distribution, whether say it is convex or not. And we can also derive density is density defined in a high dimensional ball. So it's kind of in a hyperbolic space, but it's characterizing the density of the entire embedding distribution. So apparently we think the more convex, the more robust it should be. And then the denser, the more robust it should be. And then it turns out to be that way. So here, as we just defined, the robustness performance is one minus robustness performance means, on this direction, it is more robust. Those classes are more robust. And then on to the right, it is more convex. To the downwards direction is also denser, because those two tuples are density metrics in scalar form. So as you can see, so basically we can see not say like strictly linear, but you can see it is positively correlated. So it is a good sign. So how do we use the sort of sampling based metric of convexity and then density to guide our design to protect the models? We look at mix-up. So mix-ups are, how you augment data. So cat and dog become a half cat and half dog. But in a original or vanilla mix-up setting, given one sample of a cat, you want try to find something else, it's sampled from uniform distribution. So it's quite of the naive way. But with the convexity and density metrics, we wanted to sample from less convex class, less dense class. So it's making this stuff a lot harder than before. So it implicitly is mimicking adversarial training, but it's already finishing the entire harder class or training with noise loop in the data loader. So you don't have to do a lot of adversarial training. You don't need to find the worst case scenario. The hard classes are already learned in your data loader. So it turns out that that simple trick improves the robustness by a lot. Of course, it outperforms vanilla mix-up with uniform samples. It also turned out to offer even as much of a robust protection against the adversarial training. The adversarial training here is one-step adversarial training by FGSM. So it's not say the strongest version of adversarial training, but it shows that mix-up could be a very good simple tricks like mix-up could be a very good candidate for adding to adversarial perturbation. All right, so we've talked a lot about adversarial robustness, adversarial attack, but in the end, there are toy problems. I'm not gonna try to break Alexa or break stop sign all the time. So we need to kind of dive back into the reality, which there are a lot of common noise or common corruptions. How do these models actually, what are the strategy? These kind of no one is going to do adversarial training because it's so costly at nowadays, because ChatGPT is using like millions of dollars to train. And if you retrain with noise, that is just infeasible. So what do? We want some model that comes with a clean performance and clean sort of a natural robustness. We want to find out what is the best strategy here. And there are a lot of common corruptions. For example, when you're talking to your mom and then your signal is bad, then it results in occlusion of signals like this. So your packets, network packets drop. It will drop in your feature domain, and then you have natural perturbations in a reality with categories like from blue, like blue noise, brown noise, or pink noise. All these noise could be problems. So let's tackle them one by one. All right. So it's kind of for free because we've done the comparison on all these different architectures, and so we took the same training recipe, pick the models of a similar number of parameters, make sure they're compared apple to apple, and then we test them against occlusion. So we design occlusion in a specific manner. So all the occlusion you are seeing here are masking out 50% of the information, but the masking or the maskings are getting finer and finer grain. So a famous psychologist, George Miller, said, humans has about 5 seconds of a memory, short-term memory. So we want to see how much the model has in terms of short-term memory. It turns out that the blue line here is a vision transformer type of model. It's a lot staying atop of the pure yellow line, the pure CNN architecture by quite a margin. And it's not very surprising if you add a global context like a CNN transformer hybrid architecture, it will kind of stays in the middle, right? So also CRN just another baseline. This is a state space model kind of mimicking what transformer is doing, but we can see here that the transformer architecture just has a lot more potential to be resistant to these type of occlusion type of perturbation. And the more interesting side note, as we found, is that when you concatenate all these occluded samples together to form like a broken signal, you can tell those are not real signals, but the model's performance will all of a sudden snap back, like to become well-performing again. So it is quite surprising to see this trend. But how does different models stack up against the color noise? We do see the similar trend. Transformers are staying on top. And how do they stack against the L2 norm-bounded, L infinity-bounded adversarial perturbation? Similar trend. The blue line always sort of win. So by the way, the attack we're using here is called PGD DLR, which is a form of a form of auto detect. So it's one of the state of art. So it's a variant of a PGD. So that's not just for clarification purpose. So, okay, so now we understand transformers tend to be empirically more robust against all the noise. Is there anything deeper that we can analyze, or why they're doing that? Like a promising trend is like when you learn machine learning, you always want to think about an idea of a flat minima. So apparently, like a flat minima will be like a flat surface like this. A sharp minima should be less preferable because when you take one gradient step, it all of a sudden jump out of the minimal region, then it will be really bad. So we measure two versions of a sharpness score according to the definition. So one is basically one sharpness score is measured by taking a perturbation. This time is not at input, but at the weight space. So we're nudging the gradient a little bit here and there in many directions, and then trying to gauge or do an average of a loss function. So that will give you an estimate based on the loss function scalar value that how sharp it will be. Apparently, the lower the value, the less sharp it will be, because the loss are sort of all kind of remains the same, right? So that is the first definition of sharpness score, and then will result in scores like this. And the second form is a more rigorous, but also takes up approximation. It's computing the largest eigenvalue of the Hessian matrices of the matrix. You might wonder, how do we do that? There's the method in linear algebra called power iterations. You can do an approximation of a lambda max and a lambda mean in the same time. But we see a surprising thing, which is the sharpness metric for transformer is the sharpest versus all the others, but it's more robust empirically. So what is actually going on? It seems like sharpness doesn't correlate with robustness. So we want to understand that. We took a deeper step. So we, instead of a vanilla train, so it turned out the problem is in a standard training. So if we do optimize for sharpness, there's a methodology specifically driven by the sharpness metric. If we do optimize for sharpness, there's a methodology called SAM, sharpness aware minimization. It does, you can see the model reduce the sharpness by a lot. And then it's resulting in a very flat minima. And also it turns out, because we see the similarity between SAM and adversarial training. Adversarial training, we also did the comparison for adversarial training for the sake of completeness. So it turns out adversarial training can reduce the sharpness by a lot as well, because one is doing perturbation on the parameter space, the other is doing perturbation on the input space. So, and there's no doubt that adversarial training will offer protection against the adversarial perturbations, right? So that's the point of adversarial training. But it takes a hit on the clean performance, as you can see the yellow line like starts from lower. But so it also shows you the sharpness aware minimization will offer you a little bit more robustness than the standard training. So what is going on? What we have seen here is that sharpness is necessary, but not sufficient. So if you do measure, robust aware models are having flatter minimas, no doubt. But if you use sharpness metric to measure a vanilla trained model, that does not inform you. That does not guarantee you to have a robust model. So it's not vice versa. It's not bijective. It's only one direction. So another more empirical view of because we're dealing with classification, can we visualize what is actually going on with these classifiers? What kind of errors are they actually making? So we all know, from machine learning 101 that multi-label classification is hard to draw a confusion matrices for all the classes, because if you draw it for 527 classes, you get 527 2x2 confusion matrices, which is a chaos to view. So, and if the only way is to do relaxation, if you relax your multi-label classification into multi-class classification, that also results in a very trivial case where your confusion matrix will be reduced to one line. It shows you this is 137, it's music label, everything. So the music label is bad. We know, like, the music class is bad. But if you do a top K, if you do a different kind of a relaxation, if you do relax to a set intersection problem, then you will see amazing patterns. You will see the blobs popping up. Sorry, it is hard to see in this graph. Let me turn off the light. So you will see all these blobs popping up. And what do they mean? So they actually correlates very well to the original audio set ontologies. So these little squares are music. This is a natural sound, and this is sound of things and the noise. So it shows us that a well-performed, by the way, this is the highest performance model that we have. It shows us that high performance models don't make rudimentary mistakes. They just don't confuse music with animals. They only confuse music genres with music instrument, which is very, very reasonable. Like they only make confusions in between the classes. And this shows you how do, like, we also are interested in how, what do you mean by breaking, right? So we took all these different noise to break the model. And it shows you that the models destroyed, the definition of destroyed means that here the models are close to 0 mean average precision. And we're kind of attacking the model to the highest strength to see what they are doing. So it shows you the models destroyed by occlusion are always biased towards prediction. Everything is a camera, everything becomes an alarm clock and siren. That makes sense. So you're doing these type of occlusion and everything sort of mimic that kind of distribution. And if you destroy it by color noise, conveniently, there is noise labels existent in audio set case. So everything will be biased towards noise classes. And then similarly, adversarial perturbations of a L infinity and L2 norms do different type of a damage to your model to confuse everything sometimes into wild animals or music. So it basically shows us one thing, which is that we need expert models. Okay, so I want to show you what is an example of an expert model. What if because audio set came with video, why don't we introduce a video expert? How it changes the entire performance. So this is a diff of the confusion matrices between an audio-visual model and audio model alone. As you can see, by introducing a video model, by the way, the audio-visual model can reach 49 mean average precision, which is the highest, one of the highest performing models for this. So it does add to the entire mean average precision. So as you can see, the visual experts introduced into the paradigm will improve classes like wind noise, water vehicle, and vehicles, basically sound of things classes, and then improves only on animals, dog, and stuff. But it does not really improve on anything else, and it will take a hit on the music class and then take a hit on the speech class. Why is that? Because we intuitively think, right? So the visual information for different cars and for different animals are quite different, but they actually don't help with music at all. So if we want a music expert, we need different kind of strategy. So it is really calling for different designs for mixture of an expert. Okay, so now we have a good understanding of what is robustness, what is adversarial robustness, how to deal with a real threat in reality. But there's still a lot of problems. So we talked about mix-up, but it really doesn't introduce any new data and no diversity. And canonical definition of robustness or adversarial robustness is just too hard to solve. Like, even though we try to optimize it with argmax, that equation is actually an approximation. Theoretically, you cannot find the worst case adversarial perturbation at all to do adversarial training. So you can never find it to solve it so well. And existing defense strategies like adversarial training just are very expensive. You will never ever hear ChatGPT is doing adversarial training to improve its robustness. Not only will it be terrible, but also it will be burning millions of dollars for nothing. So so what do we do from here? We leverage another foundational model, that's diffusion models. Why do we care about diffusion models? Because in the diffusion models itself is a denoiser, and then it just opens up so much potential for for potential data augmentation to generalize better into more and diverse sound. And if more and more people sort of work on diffusion, and there are more and more off-the-shelf diffusion models like Stable Diffusion or DALI for audio, then you can leverage these models to do these tasks even better and better. But okay, so let's take a look at the state of art. First thing, it's a chicken and egg problem. There's no diffusion models. There's no foundational diffusion models for audio sets. So what do? We make a chicken first. So we make our own diffusion model. So what is diffusion models? Diffusion models are basically a type of model that is by adding more and more noise in the Markov chain. And then to do denoising, to let the UNet, usually you implement it with the UNet to learn. So the model, diffusion model is really a kind of an umbrella term for that UNet. The UNet is doing the main heavy lifting work to predict, to reverse that noising process. So if you add more and more noise, if the diffusion model knows how to denoise from certain timestamp backwards, then it knows how to generate, you know, the image. Like if you do it to an extreme, when feed it with a pure noise, then the UNet, the diffusion model, will be able to generate some realistic image from the pure noise. So if you do basically that, this is the forward direction. The other way is the backward direction. So usually when you mention diffusion model, you always train it with the forward diffusion process. It's called DDPM. And the backward process is sampling from the noise. So, okay, so what is the best candidate or what is the best place to do diffusion in audio? So we pick a model that is a neural codec of an audio representation. So a neural codec means that there's a pre-trained neural network. In this case, it's a VQ-GAN. It's called an encodec model. So what it does is that basically it is a VQ-VAE plus a GANs architecture, and then why we're choosing that specific place to do diffusion on as a latent diffusion is so as you can see in a previous diagram I showed you, those are the inputs. The green blobs are the inputs that I feed into our diffusion model as equivalent to image diffusion. What they are actually latent space of that residual VQ layers. And why do we do that? Because it offers you 20 times of a reduction in parameters. So when you load your data into your data loader, it is 20 times as efficient as in loading normal features. So offers a huge advantage. And then it offers one step backwards to wave for free. So because other people already trained the VQ GAN for us, we don't need to train our separate vocoder. We just need to take advantage of the pre-trained encodec decoder. So this is how it plugs into the stable diffusion framework. We have a diffusion, we have the latent input, and we add noise and denoise, but we lack one thing. Like one thing is, what do we condition the diffusion models on? If we do this, we can only do an unconditioned model, which is basically randomly sampling from the data. But we don't have a text guidance. We can only use it for class labels to guide the model, which is very restrictive. So, okay, we look at the recent development of LLMs, large language models. We use Alpaca in this case. So how do we use it? So we only have a weak label, for example, like a shuffling cart in an audio set case. But we can use a prompt Alpaca to let it hallucinate. Then it will become people shuffling cards while others are speaking loud voice. But where does the others come from? It is hallucination. How do we fix it? We take, so because we know the visual label, the visual information from audio set are derived from that YouTube. So we can use a state-of-art video to text model, BLIP2 in this case, to extract the VTT captions. And then we can tell Alpaca to do in-context learning by creating more samples and merge all these captions into something that makes sense. So it will result in audio-visual aware captions like an audio scene centered around a soft shuffling cards of someone's hand. That makes a lot of sense. So with all these augmentation techniques, we can augment the entire audio set's 2 million weak labels into a 2 million caption data set. And then we can feed them into a text encoder. In this case, we use a T5 model. So we can leverage all these paradigms to inject new knowledge into the diffusion. So basically we can train a text guided stable diffusion model in this case for audio. And these are all the how does the prompt look like, but this is just sort of an example showing you how do we how does prompt engineering also help us in audio. And it shows us by doing this we can increase the vocabulary size by a lot. So if we do even more, we can introduce even more concepts than existing baselines. And also shows you by doing this, we by doing everything correctly, we can improve the baseline of a guided diffusion by a lot. So this is measured by fresh distance inception score and KL divergence to measure your generation quality. And that shows that doing what we did, we can improve all these metrics. So and then to give you an idea, let's hear a few sounds. That was a never striking note, and dog barking, dog calling, and then person gargling, and there's a train whistle heard from a distance. It kind of figures out. Not showing the longer prompts, but the longer prompts actually do better. I'm showing you harder cases where the shorter prompts are actually also performing quite well. So okay, we have a generative model now. We have the chicken. We wanted to lay eggs. So we wanted to generate data. What do we do to let it generate data? We do a special form of manipulation for a diffusion model called textual inversion. So what do we do is, this is a very flexible framework because we can introduce new knowledge and a new concept to this entire framework, because as we mentioned, we have a text encoder. Now we can take the last token of the text encoder, unfreeze only that text, the last words, the last tokens embedding, and then keep everything else frozen. So we can freeze the text encoder, freeze the generator, freeze everything else, but only fine tune that star correlated embedding. Then we can introduce new noise, like a new sound samples, such as teaching it with a sound of giraffe, a sound of water drop. All these things can be taught or fine-tuned into the diffusion models, and then we can let it to learn more new concepts. So here's how it works in action. So we take the diffusion generated samples, and then we serve them as a fresh training data for these previously all mentioned classification models, and how do they stack against the baseline. The first graph is a failure. Why is it failure? Because we did it naively. We thought our audio journey, in this case, we call it an audio journey to mimic mid journey, but whatever. So if we just do text to audio diffusion prompt, then we're not generating as good as of a quality samples versus the real samples. So it results in the classifier learned from these fake data actually results in inferior performance across the board. But if we did something like we mentioned just before as a text inversion, but we do it from in a way of a text guided audio to audio. Basically, audio is, you have heard about image to image editing, right? If we did it, so in a nutshell, how it works is we don't let diffusion denoise all the way from the pure noise, pure Gaussian noise, but we feed it with some initial ground, which is already a piece of audio. Let it add more texture, more diversity to it. As in this way, you can see the diffusion synthesize the data set, train a classifier on that can generate even can get a model even better performing than the baseline. And of course, the more synthetic samples you generate, the better the performance you will get. So adding 20K more, adding 40K more, 40K more are the green dots. You can see the improvements are going up little by little. This is the table showing you everything. It's a little hard to see, so we take it into a graph. So it shows you that all the way to the right side is red, is a naive generation of a text to audio, but with a textual inversion, gradually more and more. The blue dot is the model trained with pure, clean, and original natural samples. So here's the But here's the catch. You will see like the effect of diffusion augmentation does start to attenuate over time. And if we add everything we generated to the entire 2 million, it only improves about 0.2 mean average precision, which is trivial, sort of, not a whole lot. But here, the thing is that we don't have enough GPUs. In order to run a diffusion to generate 1 million or 2 million samples, we need to run it for another 2-3 weeks. So we run it for 1 week, we only generate 180K new synthesized samples. So there is a huge potential in this case for diffusion-based augmentation. The main thing is you can add more, introduce new concept to generalize to anything or a lot of things beyond that 527 classes labeled class, and teach it new stuff and let it do just a lot of potential in this. The other thing we mentioned that, what if, we try to oversample, use the diffusion to generate those very, very bad classes. As we mentioned before, like the stubbornly low performing classes, it turns out it helps. As the red line shows here, if you oversample, if you over generate on those bad performing classes, you can improve like on the performance of those bad performing classes, but also the trade-off is that it kind of, takes a hit on other classes. So it's above the, like overall, it doesn't improve the entire mean average precision, but you can fix or add some performance to certain classes. All right, so we show that diffusion is a very good candidate for data augmentation, adding diversity. So how does it help with robustness? Well, why does it even matter? So we know that, we mentioned randomized smoothing before. So it turns out randomized smoothing can be applied with a special paradigm called denoise smoothing, where you don't have to retrain a model. You can take a off the shelf if you can train a denoiser to denoise your original noisy input, then you can achieve the similar effect of a randomized smoothing. So here we are. So we have a piece of clean audio, and we have a different kind of perturbation. And so what our diffusion model is a natural denoiser. We don't need to retrain from scratch. We don't need to specifically train against a certain type of noise, because the diffusion model grew up from Gaussian noise or grew up from any type of noise. And there's a special type of diffusion model introduced last year called cold diffusion. Cold diffusion is the idea of you don't train it with Gaussian noise, but any type of other noise also serve the equivalent effect of Gaussian noise. And it turns out that is coincidentally shares a very similar intuition as our masked autoencoder. It turns out by cold diffusion, it is equivalent to our masked autoencoder. Our masked autoencoder's noise is masking out is mask. Mask is one form of a code diffusion, and it just plugs into the code diffusion framework nicely. So basically, we can use we can use all these different diffusion models as we train to denoise, and then denoise the noisy input into clean input, and then we can feed it into the classifier. The classifiers here are not adversarially trained; they're just the vanilla classifiers. And then we see, and then we do majority vote, following the randomized smoothing framework, and then we can get a robust classification paradigm in this case. So here are the results. So the red line, as here the audio journey, AJ means it's trained with one-dimensional wave, so it's diffused with the noise directly on wave, and LDM is the LDM as we mentioned, and cold diffusion is the masked autoencoder in this case. As we can see, so for the sake of a good comparison, we also train a randomized smoothing model for the sake of comparison. So as we can see, the diffusion models, the trained with a noise offers more protection, surprisingly, against the randomized smoothing. So it does boost up a lot of the performance of the undefended classifier. Undefended classifier here is the blue line. So it's really bad at facing colored noise. And the same thing happens for adversarial perturbation. So the denoise smoothing really give us a good guarantee and a good sort of a theoretical guidance. But then if we use diffusion to replace the pre-trained denoiser, that is a very good candidate for defending against the adversarial perturbation and color noise. But the more surprising trend pops up when we're trying to defend against occlusion type of noise. The other type of noise, because they grew up in Gaussian noise, they were trained with Gaussian noise, they are only good at denoising Gaussian noise. If you occlude part of the information out, they are not able to reconstruct that well. But as we just heard before, mass autoencoder is super good at reconstructing the original signal given the occluded portions. They are just natural defender against the occlusion. So the mass autoencoder can be way more robust than any other type of diffusion models fending off occlusion type of noise. So, all right, so to kind of let's take a final step and take a look at what we have learned. So different noise in reality takes different type of defender. So if you only care about adversarial perturbation, that kind of defense might not translate to other type of defense. But it really depends on your task at hand to design a defense. Like it depends on the threat model you define. Like what kind of a noise do you care about most? Then you defend accordingly. And also, transformers architectures are just naturally more robust. And diffusion models are very, very strong candidate to opens up a huge potential for data augmentation with diversity, and also, as we shown, are natural defenders to these noise. So, as we also talked about in by visualizing the confusion matrices, future of the audio classification should be in a mixture of an expert paradigm where you plug in music expert, sound of things, or natural sound animal expert and things like that. You can design specific training techniques to gear towards those type of model. And if we could develop a unified view of a cold diffusion versus hot diffusion, because hot diffusion has a nice theory background around it by physics motivated Langevin dynamics. But if you do cold diffusion, none of these exist. So if we could analyze more of a theoretical framework to bridge all the gaps, that would be very nice. And so by the way, the diffusion models used for denoising, here we adopt one of the recent literature of doing one-shot diffusion. So we don't do the full DDIM reverse steps. We only do it one shot, picking one specific shot. So also, there are many different type of denoising samplers. Some of them are based on pseudo numerical method, like a Runge-Kutta method to approximate the diffusion process, but we don't know which one is actually the best candidate. So if we do more work on that, that will also be very promising. So here are the list of my past work in my PhD sort of a journey, and this is a sort of a delta or more work, additional works that I've done from my thesis proposal to this stage. And thank you for coming here. Thank you for your attention. Special thanks to my committee members. Thank you. If you have questions, we can start. Thank you.
All right, thank you, Billy. Great presentation. Very, very interesting, very comprehensive, given your work. So at this point, we'll take questions from the committee. Dan, would you like to go first according to LTI tradition?
Yes, that sounds fine. Hang on, just trying to go over my questions. Okay, yeah, thanks very much, Billy. That was a beautiful presentation. Very, there's a lot of stuff, right? You've done a huge amount of stuff, so it's difficult to take it all in. But it's everything you showed was great and very, very interesting, and I really enjoyed it. Yeah. Obviously, I'm very interested in AudioSet and the developments within the community in terms of improving the performance on it. You have focused on MAP as one metric.
Yes.
As you know, in the work that we've done, we've actually not looked at MAP, not prioritized MAP, and looked at other metrics. D prime, which is just a measure of per class discriminability, is not that different from MAP, although I think it's better. But the other metric we use, which is this LOLRAP thing, which is a label ranking average precision, is much more interested in not within class discrimination of positive and negatives, but between class discrimination, that is the calibration of different scores. I don't think you've looked at any metrics that use that. When you looked at the confusion matrices that look at the top K things, that's getting closer to that. But I worry that all the work that's been done by the community on AudioSet has kind of blindly followed this one metric, and I wonder what you think about the risks of optimizing MAP when it isn't necessarily going to give us a useful classifier, particularly if we don't deal with the calibration between different classes.
Yes, that's a very that's a very deep question, and also a very good question. So MAP, to reiterate, MAP, I would think, is also a pretty well-established metrics in the statistics, like theoretical setting. So it's basically a mean value of average precision, which is taking the numerical integration of the area under the ROC curve. So I would say it is an conservative, it is a conservative way to estimate the balance between precision and recall. So I would say yes, it does have a potential oversight, but so far, because the MAP are not even reaching like a very high regime in terms of audio set. So I guess the community, like if we measure against MAP for now, it is okay as you observe, but maybe later on when these models are getting less and less confused about within the class distribution, then we can shift to other complementary metrics. But for now, I think if we could still tell the big difference between model A and model B by measuring mean average precision, that still might serve us well in terms of an overall sort of a gauge against these models, because as I mentioned, like an apple to apple comparison is pretty important. Otherwise, we wouldn't know what are the important part of the recipe that you need to adopt to make a model perform better.
I think, yeah, I think that's a good answer, but the reality is all this stuff, we're well into, I believe we're well into the regime of just fighting against quirks in the audio set labeling. The audio set labeling is extremely, as you've shown, it's extremely imperfect. For many, the actual labels themselves are not that great, but the categories have all kinds of problems. You use the example. Okay, I'm just going to give you an example. I'm just going to give you an opportunity to talk more about your insight into AudioSet. You raised at one point you drew attention to the fact that in one scenario the speech conditions, male speech and female speech, were particularly poor performing classes.
Yes.
Why do you think that is? So I think you said something about why it is, but I have an idea of why that is. I just want to hear what you think it is.
Because the speech label are too prevalent in the entire audio set distribution in an unbalanced set. So the classifier doesn't learn enough of a male speech and doesn't get to see enough of a male speech versus female speech, but then it all biased towards predicting speech. And essentially, if you predict male speech and female speech as speech, that is okay. It is still, practically correct. So as we showed later, like in a diffusion case, if we do oversample on these bad classes, we could prove to boost up the performance and debias the classifier a little bit. even though it's not a lot, as I showed later, like the trend does go up. So I would say there are ways to fix it by a little bit, but entirely eliminating the such phenomenon might be hard given the extremely unbalanced distribution of audio sets.
Yeah. I mean, but I just want to make the point that it's not just that there aren't many examples of male speech labeled in the data. It's that there are a million examples of speech, many of which are in fact male speech, but which are not labeled. And so it's a problem of these, you know, the labeling level of labeling hierarchy of the labels, that you know, the model's been shown order of a million examples, or so, you know, order hundreds of thousands of examples of male speech which do not bear the male speech label. And so of course the classifier is extremely confused. It says, you show me male speech 1% of the time, you tell me I should call it male speech. I don't know what to do. And so, you know, those are the kinds of things that they're just like the quirks of the labeling that we did. And I worry that we, you know, I'm totally responsible. I'm 100% responsible both for the problems of the data and for encouraging people to use balanced metrics that give equal weight to these very rare classes. But, you know, I just don't want us to be blindly going in and optimizing for them when it's clear that there's other problems going on. Okay, sorry, I'm editorializing. Let me ask you another question. In the work on measures of robustness, predicting the difficulty by robustness, you came up with two measures, one based on convexity and one based on density, right?
Yes.
Yeah, the next, the plot, the ordered plot, yeah, this one. So so each class has these two properties,
yes,
convexity and density, but you're plotting it just on the convexity measure. Why that? And
the density measure is showed here in the tuples. Those are showed.
It's printed, but it's not, doesn't contribute to the position of the points, right?
Yes, so it is hard to show three things all together. We were
Absolutely.
just doing...
But I'm interested because you chose to do it this way. Why did you choose this plot as opposed to some other plot? You could have added them together or something like that. I don't know.
It's I think to be honest, I just want to show everything in one graph and then show like if they have a correlation or not. So if we plot it against the density, I would probably think it will be a similar trend. It's a noisy linear correlation. It is not strictly, as you can see, all the label distribution, but there is a underlying correlation there.
But I noticed that on the points you've pulled out, the values of the two indices are very similar. If we plotted the density index versus the convexity index, what would that look like?
That should also be a sort of a linearly correlated thing. So the density labels here, the labels are two quantiles of density. So here, on the top right hand side, you can see row 60 and row 80. That stands for the high dimensional ball's radius. So we want to see what is density inside of a certain radius of a ball. So that is really sort of complementary. So I'm pretty sure that if we plotted, density versus convexity, it will.
Oh, I see. So the numbers are just two versions of the
density metrics. Yes.
Got it. I see. I misunderstood that. But what I'm interested in, whether there's an intrinsic correlation between the two measures, that they're differently motivated, but I wondered if your observation was that they tended to give the same result, in which case is there something deeper going on that means that convexity follows density?
I haven't done like the specific studies like analyzing their difference, but I could tell, like, as this graph shows, like they're both intuitively and also like empirically correlated to the robustness definition as we mentioned. So like the point is that we want to get some guidance for mix-up instead of just sampling from uniform distribution or multinomial distribution of the labels. So this will sort of inform us to select the hard classes. Like it is more like targeted select versus selecting blindly. That is the core.
I got that. I like that. It makes a lot of sense to me. Okay, one more question. In the diffusion stuff super exciting. Really, I hadn't seen, I hadn't seen this until recently, and I really like it. Can you just explain to me the noise model you're using in diffusion? As I understand, the diffusion is in a tokenized domain.
Yes. So the diffusion is in the in codec embedding space, as we see here.
To noise up samples, when you're training the denoiser, you have to generate noisier examples.
Yes. So
what is the way how do you make a quantized, a tokenized stream noisier?
So so the encodec model, pre-trained encodec model will provide us with an encoder and a quantizer. So we just need to pipe an original audio into the encoder and a quantizer.
So you're saying that the noise model is make it noisier in the waveform domain, and then just see what the code.
There were a lot of noise.
I'm sorry. We don't hear it.
Okay. I think it should be okay. Maybe I should is there? Sorry, there were very loud noise.
Yeah, I'm hearing it too. I don't know where it's coming from.
It should be fine now, I think. Can you hear me? Cool.
Yeah, I can still hear you, and I haven't heard a noise for a couple of seconds now.
Cool. Sorry. Yeah, sorry for the glitch.
No worries.
So I was just asking about how you where you apply the noise when you're making noisier samples in the.
Yeah, I am applying the noise onto the post-quantized embedding of this encodec model. So you get a pre-trained encoder, you have a pre-trained quantizer, and if you do the dequantized version, then will result in a 128 by 504 feature embedding of that pre-trained encoder. So you will get an encoder, you will get to that post-quantization embedding space of the encodec model. And this is where we're doing latent diffusion on. That's the whole point of latent diffusion. We're not doing diffusion directly on the raw data input, but on the latent dimension.
But then the denoising network operates in the full continuous embedding space?
Yes. So the denoiser will work on the post-quantization space as we are showing in this graph. So it's basically denoising this.
Yeah. So then why is this, where's the efficiency gain due to using the quantizer?
The efficiency gain is really about when we implement the data loader, we don't need to load all the wave files. We can load these code books instead of the wave files. So when we load those models, load those data into the data loader, the space it takes are 20x smaller.
Okay. Why is it so expensive to do the augmentation?
Because running forward diffusion is also quite expensive on GPU. So if you have because of the sampling process, as we
Sure.
talk about for diffusion, it's a lot more expensive than GAN. It's not one step, so you need to do it certain steps. In our case, 20 to 40 steps in terms of doing DDIM or PNDM, which is the approximation. So each one sample takes 20 to 40 steps. That will be a lot of burden when you do it on the large scale to generate millions of samples. And
I really wanted to hear some examples of these augmented things. Why didn't you play any?
We do have a lot. I can show you offline, but so
can you say, just can you give us a gloss on what they sound like? Do they sound natural? Do they sound weird, but they help anyway, or what?
They sound a little more noisier than the original ideas. So basically, for example, a sound of a water drop will be more noisy than the original water drop. So it will be mixed up with other sounds. So it was a not ideal quality, but I can send it to you right afterwards to show you like how do they sound like. So
yeah, no urgency. Just like I'm super curious, right? Because you've shown that they are helpful in terms of augmentation, which is, it's a big deal, and it seems interesting. And it's like makes me wonder, like, well, what is it they're really adding? How is it the diffusion model is able to add some useful information to help generalize the model? And so, makes you wonder what they sound like. But just curious. Love to hear them. All right, thanks. That's enough questions for me. I'll let someone else have a go.
Thank you. Thank you for the wonderful questions.
Awesome, thank you. Emma, would you like to go next, maybe?
Sure. Yeah, so I'll get right into it. So I think my first question is about the exploration of sharpness in chapter 12. And so you measured sharpness according to, two different sort of prominent metrics across different neural network architectures. And yes. I was wondering how that's possible. Like, I don't think, like, are those numbers actually comparable across different architectures?
They are,
because they're kind of dependent on the loss scale, right? And loss scale tends to not be comparable across different models.
That is also the problem that I want to bring up with the current definition of sharpness. There's no universally scale invariant sharpness. So what we did implicitly is we tuned the row score. So if you measure the row, like here, there's the row controlling the epsilon, which is the tiny nudge you bring to the weight space. So apparently different networks have a different loss landscape. So the row is different for different type of models. So that will result in a sort of inconsistent comparison. So what we did here is we for the sake of fairness, we use the same row for all these different architectures. It is a one way of a fair comparison, but it's also unfair in terms of measuring scalar values across different models. But also currently there's no good way to measure this score across different models to bring it into the same scale. So we are just reporting based on what we have seen. So in this case, the reason why we wanted to compare lambda max, which is the largest eigenvalue in the first place, is because we do think computing that metric might be a more fair apple-to-apple comparison in this case. And that also shows like the vision transformer does have a sharper minima according to the power iteration approximation of sharpness. It's not it's basically validating, like, the sharpness score we compute by averaging these loss values are somewhat informative, but everything needs to be taken with a grain of salt. But it's we are, as we show later, if we do SEM or adversarial training on these, both of metric will improve drastically. So it does correlate with the smoothness of the loss surface. So all we are saying is here, if you measure sharpness blindly, as we did here, like it's not blindly, but if we do not know what networks are we measuring against, we measure it with the same row, then we'll run into the problems that sharpness might not be that informative of telling you whether the model is actually robust or not. It is not a good prior notion to use, or it doesn't, if you measure blindly, it doesn't tell you how robust it'll be by just judging by its sharpness score if you measure from vanilla approach.
Okay, so do you think that we can conclude like confidently from these measurements that the loss landscape doesn't play a role?
It does. I mean, it certainly does. We are showing that robust models having flatter loss landscapes, no doubt. But if we just measure with the current definition of the sharpness, then we probably wouldn't get that conclusion very easy. So that's what I am claiming here. It's like we need to develop probably better sharpness metrics, as you suggested, across different models. Maybe not use a same row for all the models, but kind of develop a scale invariant sharpness metric so that will be more fair to evaluate against the different type of models in this case.
Okay. In the conclusion of this chapter in your thesis, you do say that you think that there's not a strong correlation between the loss landscape and the model robustness, and that the robustness is not necessarily tied to the characteristics of the loss landscape, though.
Yeah, I think that conclusion was a little bit of, say, like blanket statement I made, but in the end, I think I really discovered that the sharpness is just necessary but not sufficient condition. I think I will change that overall claim in the revision.
Okay. Okay. So, and I have another question. So, so I think in your proposal, I think one of the questions that I had was sort of like, what are your like whatever 3 to 5 like high level takeaways that you have, from this on, how to successfully build a large scale audiovisual learning system. And I think that you provided that in this presentation in slide 69. And I was wondering if you could say some more on how this set of takeaways that are the set of takeaways from your dissertation work connect with your vision for the future. So your vision for the future is very much, I mean, my interpretation of it is very much sort of like diffusion models are going to maybe solve a lot of the problems here. And so I was wondering if you could comment more on, connecting these takeaways with, remaining problems that diffusion models, will solve, and what remaining challenges will there be that diffusion models will not solve?
Yes, that is a very good question. So I would say, diffusion models, as I claim, like it does hold a super strong promise for future generalization and then robustness, but it also comes with problems of inefficient sampling. So I would say only till those problems can be solved, then if diffusion models will sort of take over. My work just shows like the progression or the evolution from supervised model, which is a very limited paradigm, to self-supervised, and then gradually improve to diffusion model. I'm not saying like there's a single paradigm which will dominate everything, but I would say like as long as we keep introducing more and more flexibility of the model training paradigm to allow people to add more information in throughout the training process, like diffusion model is allowing you to add a textual guidance. So that kind of model eventually could inform future design. And I would say those those are the trends we've been seeing that could help with a future generalization or helping robustness in the same time. Like if you just do it for with a very limited architecture with a set paradigm, those don't tend to bode well for future generalization or expansion, I would say. So that's the sort of the trend I've been seeing.
Okay, so you're saying that the main challenge that we've had that, you know, this generation of models and maybe future generation of models will sort of help open up is like the flexibility to sort of incorporate information from maybe different modalities or like in different formats.
Yes,
Is that correct?
That's what I think that's my take on this.
Okay, do you think that then do you think the lack of flexibility or like the sort of key problem is in the architectures that we're using? Do you think it's in you know, our optimization strategies, or like maybe is it in our like in representation space?
So yeah, so I think like the reason why I say diffusion models are so promising is that it sort of opens up the optimization process, right? So we knew from back then that training with noise is probably better than training without noise, but it gives you the flexibility to fine tune these noise, to couple the noise with some other conditional information such as textual embeddings. So I would say to this end, I would say the model architecture, the entire paradigm does make a difference. If you only focus on let's do a design a black box model by itself without knowing what is going on, then it's probably very limiting in terms of the things the model can do. That's also why VAEs are sort of not preferred these days, because they need a very set architecture. They need a very rigid paradigm. Like you need to encode everything into Gaussian, and you don't have any way to kind of open up the black box. So I think maybe diffusion, like as I cited, like code diffusion is a good direction to think. Maybe diffusions don't need all sorts of Gaussian noise, but can be a sort of informative inspiration to design models that encourage sort of coupling information to fuse together throughout its optimization process. I would say the optimization process, the model architectures are really coupling factors, and they're all key parts of the components to make it successful in terms of generalizability and robustness.
All right, that's all I have for right now. Thanks.
Thank you.
Great, thank you. Shinji, do you want to go next?
Sure. Can you hear me?
Yeah.
People in the Zoom.
You're hard to hear in the Zoom call, Shinji.
Is it better?
This is much better, thank you.
Yes. Okay. Sounds good. So first, I would like to mention that during the proposal, I was actually asking Billy for improving the presentation, and still a little bit the presentation is in the very packed side, but I see some improvement in terms of reducing some contents and showing some kind of a high level concept and so on. So I see some improvement, which means that you can do it. And well, as a kind of a thesis defense, it's gonna be sufficient, but I really want you to improve this kind of the skills more. This will make your kind of research life even stronger. This is the first comment, and the second the comment is today's my kind of a comment today is mostly high level, by the way, because we already have a couple of discussions about technical stuff. So today's presentation, you mostly talking about the robustness that in the input side or architecture side. But there would be a kind of another dimension of the robustness, which is for the task in the output. Like, for example, if we changing this task to the sequential generation, like audio captioning and so on, whether we can have our same conclusions, same discussions, or whether we can have the different methodology we have to develop. I just wanted to discuss about this, the output robustness perspectives.
Yeah, these are first, thank you for this deep question. So I would say, as I sort of clarified in the beginning, my thesis were mainly focused on input robustness.
Yes.
And output robustness, I would say, is a different devil, because you get all sorts of why did I focus on input robustness? Because it's easier, relatively more straightforward to analyze. We know how much input changes output. That's a very straightforward and then theoretically sound definition of robustness. Whereas if we deal with output robustness, then the models are just subjected to many other perturbations within the network, because it's all nonlinear, non-convexity. There's no way to analyze that deterministically. So empirical evidence on certain output models might not apply or generalize to other things, whereas input robustness should be a more set paradigm for us to follow. But if we choose to analyze output robustness, then we will run into all sorts millions of more problems where the complexity gets high, and then you just don't have a good tool for now to analyze the output robustness. For example, if we try to analyze CTC versus or other sequence prediction tasks, then we run into all different symptoms of the probability all of a sudden nudged a little, and then we'll jump to other cluster, and then we'll just predict very wildly different. I would say that part requires more work from the community, and I would say people need to have shared tasks on those things to tackle them one by one separately. That it is unsolved for now, in my opinion.
Okay. Related to the still high level, related to the following, related to your the discussions, you know, the NLP communities now are moving toward to solving the many tasks in the single model, right? And the speech, the community also, they're having such kind of activities, and there are a lot of actually successful directions of using single model to solving the multitask issues in the such kind of areas. And I just don't fully follow this part in the, especially in the audio, the classification, the community, DKS community, and so on. Are there such kind of activities of, like, for example, just, you know, the combining all the DKS tasks and making it just one leaderboard? Is there such kind of activities? I'm just curious about it.
Not at all for now. So I am also kind of disappointed on that. That's why I was hinting on, like, if we could so this is all due to the I would say all inspired by the work T5, right? So everything can be formulated as one prompt, and then many different tasks of NLP merged into one. So, but there was no T5 in audio or in speech back then. So
speech some actually.
Yes.
I just don't know audio side. Dan, do you have some comment about this? The single foundation model. Yeah, go ahead.
I think it's a good insight. I think it's a difficult thing for people who have been specializing in single tasks to really, to embrace. And I also think that you know, the scale of the models is a challenge. That, you know, most people working in this area don't have, you know, are compute limited, and so then moving to a large foundation model is harder.
Yeah.
You know, I don't know. You're making me think about it, and I'm thinking like, well, so what would that mean? Because I don't really want to do it myself either, but I hear what you're saying about how it's this very powerful development in language modeling,
Sure.
and needs thinking about.
Okay, sounds good. Yeah, I think that's gonna be also very interesting future direction that you can also think about in your long-term research. You know, thesis is not this is an important goal, but still in your entire life, one checkpoint.
Yes.
With that, you need to actually build a lot of more kind of from now on, you need to actually build your research agenda by yourself. So this kind of direction would be also another interesting research topics to me. So the next question, again, I try to pick up some of the high level one only. So you said that maybe goes to the 31,
Yeah.
31st and the 32nd. Convexity measure and the mix is a good matching, you said, right?
Yes.
Since it is, yes, very similar, so that's why, right? So can you go to the definition of the convexity?
Yeah, so basically in the embedding space, we can kind of connect two dots in the embedding space, and then take that middle dot, which is non-existent data from the original data, and then pipe it into the pre-trained classifier, and see if that classifier output the same label as the two dots of the original dot.
Probably due to the set the time. Not sure. You can do it again.
Yes, I think so.
So this means that the doing almost same input to measure this kind of a convexity. You actually prepare some different sample.
Yes.
And then getting the output. Where's this space, by the way?
So this is just a embedding space of a pre-trained classifier. It's how you, similar to you measure an inception score. You have if you're familiar with the inception score. So you get the bottleneck and then you connect it. You just compute an average.
Oh, okay. It's not the pre-activation before the final rate.
No. It's
okay.
Just
so then this is actually a little bit different, right? Because mix-up usually consider the convexity of the output class, right?
Yes. So what we're saying is
that's actually my question. Yeah, it's first hard that it's very straightforward, but I found that it's from this figure I am not very sure which space are you talking about. So this will be a difference, right? Yeah.
So all we're saying is that if we could have a sort of a easy way to guide the mix-up, or as we said, the vanilla mix-up is pure uniform distribution.
Sure.
You're sampling blindly from the entire data set. And
Correct.
in an audio set, you're always sampling music and speech, which is not helpful. So what if we make the task harder? And then what are the harder class? Though we're saying that these could be good indicators for us to find harder samples to mix together with.
Oh, I see.
Yes.
That's why you kind of changing the mix based on the relationship.
Yes.
Okay. So that it's actually improve the performance of the convexity. This corresponding to improve the robustness.
Yes,
Got it.
exactly.
Yeah. Thank you so much. Yes, that's the clear discussion to me. And the last question. So you use the diffusion in two ways. One is to using it as a data augmentation, right?
Yes.
And the other is to use it as a denoising, like
Yes.
using a reverse or whatever, right?
Right.
And it's again, it's more for the high level question. This is actually quite the typical the methodology of the noisy speech processing, like a noisy speech recognition. Whether we should work on making the model to be close to the noisy data by using the data augmentation, versus whether we try to make the model to be canonical in the speech context, which is going to be clean. And then making the data to be also in the clean side, and then making, anyway, both of the cases, we can make some kind of matching, better matching between the model and the input, right? And then my question is, with the diffusion, is there this kind of the methodology can be changed? I mean, since before that, we actually using a different technologies. Data augmentation side, we just using the collecting the noise and using the room simulator,
yes,
or whatever to make a kind of a data to be the augmented. While in the noisy, the denoising part, the used to be a statistical model, but anyway, currently we use the deep neural network based models. So the model is very different, but the currently with a kind of a diffusion based the approaches, at least the not same model, but the fundamental the methodology behind the denoising and the contaminating can be unified, right?
yes.
With this kind of work, do you think we can unify these kind of two methodologies, and they can? By the way, my another kind of the experience is should do both. Do the kind of data augmentation, do the kind of denoising. These both are kind of actually important. And do you think that with this kind of direction, can we unify these two the methodologies in one formulation?
I think it might be possible, but currently, as I briefly touched upon is that if it is reliant on the sampling process of the diffusion.
Sure.
So if we do full sampling, then it's kind of prompting the diffusion model to hallucinate more and more, adding more features.
Yeah.
But if we want to, as we mentioned, if we use it for denoising purpose, then one shot or a few shots are fewer steps are more preferred, because we do not want to actually let it hallucinate more.
Right.
But if we do have a sort of a sampler or develop new sampling techniques that are aware of these needs, there might be possibilities for us to unify all of these things into the same model framework. And then, as you said, that diffusion model could probably tackle not only noisy speech, but also clean speech, and also could serve as a sort of a future say like a one model for all, for basically tackling all these different tasks, and be a generalizable solution.
Good. Yeah, that's going to be also another very interesting methodology. Yeah. Okay, that is for me. Thank you so much.
Thank you.
Great, thank you. All right, I'll be the last one to go before we open up questions from the audience. So let me be brief. On slide 36, we have the biggest difference is really if we add noise to the waveform, they're all the same, all the four different methods. But if we add noise to the feature, the VIT and the resonant do better than the CRNN and the CNN plus transformer. Now, I understand why VIT acts strongly to adding noise to the feature, but what about the ResNet versus the CRNN? I don't quite understand this behavior.
Yes, this is a peculiar sort of a phenomenon that we observe, but I believe it is not an error in my experiment because I have replicated many times. I try to understand that, but it just so my current explanation is that it is very bizarre. Like as we see the noise on the two, so my current explanation is that the hybrid models are somewhat different than these just either transformer or CNN families models. Like their robustness needs to probably we would expect them to be the middle ground between CNN family and then transformer family, but they probably do have a different their learning units are different than either transformer or CNNs, because CNN's learning unit is kernels. They are doing just learning based on what the kernel sees, whereas the transformer is based on what the patch covers. But the CNN and CRNN and CNN plus transformer, they are learning from the kernels, but they also have a global map. So they might, in this case, they get affected by the damage to the feature space more than those pure models. So that is my current analysis, but it is certainly a very weird phenomenon that we're observing in our experiment. And I did run the same experiment a couple of times, and we do observe very similar trend, which is a sort of a hard to explain phenomenon.
Right. I mean, maybe what we need to do is not run the same experiment many times, but run similar experiments that are designed to test this hypothesis and tease out if it is indeed the global context by trying out other models that have global context or doing CNN plus different types of transformers and see how they behave.
Yes.
All right, no, that's a good answer. Thank you. All right, so at this point we've had the committee has had the opportunity to ask questions. So now, customarily, we also allow the audience, invite the audience to ask questions. Do we want to start with people in the room first?
Yeah, but better to be here, and then the viewer.
Yeah, absolutely.
There is one question from the audience here.
Okay.
Say again, Shinji, please. There's no questions?
One question. Yeah, go ahead.
Okay.
Yes.
Yeah, hi. So you mentioned in your second part that that sharpness is a necessary but not sufficient requisite for having a more robust model, right? And I think that intuitively makes sense to me, but I'm wondering about that not sufficient qualifier, right? So like from a qualitative perspective, what are some what properties can a manifold have in order to sort of lose that robustness but still be sharp?
Yes. So that's a perfect question. Actually, along the line with what Emma asked me. So I was struggling with the claim that I made before in my thesis, which is a blanket statement saying there might not be a lot of a correlation. That's a seemingly. So, but after it's the same line as that Emma's question, which is how is sharpness measured? So the current measurement of sharpness is different model by model, scale by scale, and they're not even the same fair measurement. Even we claim, well, it is fair because the parameter for all the models we use are the fair of rho equals to 0.05, but it is really not guaranteed to capture that loss landscape. And if you say if we measure sharpness by visualizing the loss landscape, then it is even more of, say, a vague statement, right? So I would say the current definition of sharpness is not scale invariant, which renders it sort of less informative for us to gauge its real sharpness of different models as of now. Like if you say we need to fine tune a row for different models to measure sharpness, that would be very hard to convince others that's an apple to apple comparison, right? Because so I would say that we need a better definition of a scale invariant sharpness definition. And it's not saying sharpness and the robustness are not correlated, or what we're saying is the current definition of sharpness is necessary, but not sufficient to indicate its robustness. Like it's about the current definition of sharpness. Like I should really add a quotation mark on the current definition of sharpness. Not saying that we understand. I don't think anyone would understand the real sharpness of a model without really doing a whole set of experiment on that. Only measuring it by one metric might not be a very good view to this problem.
Okay, but then like even from like a geometric perspective, a geometric intuitive perspective, like looking at something where like you have a nice sort of stable-ish, flat-ish quality, you know, near your maximum or minimum, right? Like I'm trying to picture that, and I'm like, oh, that's perfect, right? That should just be robust. Why isn't it?
So we are showing that robust models do follow that.
Yes.
The robustly trained models do have good sharpness.
Right.
It's just that we might not capture that with the metric itself.
Got it.
That is what the problem is. So I would say it is the problem of the current definition of sharpness. That's also I want to change my claim is on the definition of sharpness is a little problematic. So that doesn't allow us to capture that robustness. So if you measure it with the average of loss, for example, different models have different loss scale. So how do you even compare fairly on these? Even as across different model on the same task, they also result in different task loss scales. And as I said, like the approximation of the largest eigenvalue is also a very, very approximative, it's power iteration. So you are not guaranteed to find that lambda max or lambda mean very accurately. So it is, none of these will capture it very correctly. But I would say the flat minima notion is still should be correct. And then the robust models do have flat minima. This is definite. Like,
got it. Yeah, that makes sense. And then just a second question before I'm finished. How useful is the idea of measuring convexity for smaller classes? Right, because you talked about like trying to find,
that is a very good question. So we are showing you in the beginning the curve of all these different classes, right? So this is a sort of a hidden devil in audio set, because the metric is mean average precision. So everything is meaned. So for the smaller classes, I haven't looked specifically into it, but our hope for that is it will improve most of these middle or average classes. But it is very interesting. I certainly agree. We could look into more of, say, fewer classes and then the edge cases and then see how much do they specifically improve the robustness. But overall, I think what we're showing is overall after the mean process, then it will improve the robustness about basically have a blanket sort of effect on everything, but not specifically, we haven't specifically looked into any of those smaller classes. It will be promising to look into those though.
Thank you.
Thank you.
Cool.
Awesome, that's great. Thank you. No more questions from the audience in the room?
No, we don't have any question in the audience.
Okay. Then other remote participants that would like to ask a question?
Oh, I saw a question from Gus asking what kind of adversarial attack is that? That is as we explained, that's a projected gradient descent attack. PGD-DLR is the adversarial attack that we're using.
That's in the chat. Okay.
Yes.
Okay. Any other questions from
So
Zoom?
there's one question.
One more question.
So yeah, I just wanted to ask, like, you look.
Yeah, you can come closer, Arina.
Yeah. So yeah, great presentation. I just wanted to ask, like, so you've looked at the robustness from the input side,
Yes.
and also I think Dan mentioned about the calibration.
Yes.
Did you have you seen like what happens when you study these adversarials
Yes.
inputs, and what happens to the probabilities outside at the output side?
Absolutely. Great question. So we're talking about so the question is, have I looked into the calibrated scores of the performance of an audio set? So first of all, like as Dan asked, like the community or all the standard benchmark are not on the benchmark of ECE, right? Like the calibrated score. It's on mean average precision. So we were not. If we were to content on the leaderboard, that was not a favored metric, but I did look into this previously before. It wasn't written in my thesis. I would say it does change the model's performance, like the metric against ECE quite a lot. As you can see from these kind of graph, like in the confusion matrices and in a class performance metric, but since it was not a standard metric, it is hard to convince others that making progress on the other alternative metric is meaningful or not. Like you get one model, you can measure the calibrated score, but if we were to make improvement, we first need to report mean average precision, right? So that was the sort of also the sort of sticking point was there. Like the community was so much bogged down by mean average precision. So everyone is contending, even nowadays, it's still a hot leaderboard. Everyone is contending on the mean average precision, but I think we need a sort of a set of experiment to advocate for a strong case of ECE or calibration scores. Then we can convince more and more people in the community to adopt this metric as a standard metric for audio set to replace, because there are, I mean, mean average precision, even though it might have problems, but it still is an underestimate of your area under the curve. So you say it's not fair, but it's underestimating. So it's kind of fair in the other way. So
some kind of lower.
Right.
Yeah.
So I would say we need to do more work in the community.
But like improving robustness should improve somehow the calibration properties as well of the model.
Yes, I believe so. And I have looked at it once before. I did find, I think, you know, in terms of if we measure against the calibration metrics, the robustness do correlate with that. Thank you.
All right. Any other questions? All right. If not, Shinji, would you be able to, or first, please stop recording of the presentation.